All right, I'd like to talk about projectile motion now. This is a very common special case of XYZ motion. Mostly we're talking about two dimensions here, but we have gravity operating on a particle. If it's fired and it now becomes a projectile, it has a trajectory like this. Gravity acts in this direction, pulling it down, but there aren't any forces or anything slowing it down in the x direction. So what we'll consider is that velocity is velocity is constant in the x direction, but it changes in the y direction due to gravity. So it'll have some velocity here, it'll get slower in the y direction, and then come back down again. All right, our origin is usually defined where we start. It'll have the initial velocity will have a magnitude and a direction. The direction in the x direction would be the velocity times that cosine, and the velocity in the y direction would be the velocity times the sine of the angle. All right, I want to remind you of our constant acceleration equations that we have used before, and that when acceleration is constant, these three equations apply. When acceleration is zero, or velocity is constant, then this is really the only equation that applies. So this is the equation that applies in the x direction because acceleration is zero, velocity is constant. These are the equations that will apply in the y direction because gravity is constant. What we'll do in these cases, however, we'll assume that a is equal to minus g, because usually positive direction is going up, and so g will generally be in the negative direction. All right, so with that, let's look at how we apply those equations in projectile motion. Virtually all the problems start like this, where you define what's happening in the x direction. We say that x is equal to beginning x, which is generally 0, times velocity in the x direction times time. The velocity in the x direction is equal to v cosine theta. And in the vertical direction, virtually almost all of them start with this equation, which will say that y is equal to y sub 0. And this is the ending y at the end of our problem. This is the beginning y. And the velocity in the y direction will be equal to velocity times sine theta. The time when you would use this equation would be if you're trying to find the velocity at different points along the path based on some time frame. And when you would use this equation would be if you're trying to find the maximum height. Most of our problems are going to be where we're going to be dealing with this, but occasionally we may need to find the maximum height or use the maximum height to find some other piece of information, and sometimes that. All right, so let's do a problem. Let's do this guy right here, and we have this ball, and it's being thrown by this player. And it says determine the time for the ball to strike the ground, it's observed that it takes the ball 2.5 seconds to get from this point to this point and strikes the ground. We need to find out what the speed and the angle is at which the ball was thrown. All right, again we'll start with the x direction. It's almost always where I start anyway, and we'll set it up in this form, and it makes it generally pretty easy to follow the work that. So in the x direction, we're going to say that x is equal to x sub 0 plus vx times time. And x is the distance that it goes, so that'll be 50 meters is equal to 0 plus velocity in the x direction would be the velocity right there times that cosine of angle, so it'll be v cosine of theta. We don't know either the velocity or the angle at this time, but we do know the time. We'll fill that in just a second. All right, in the y direction, then let's start with the equation that we just said. So y is equal to y sub 0 plus v sub 0 yt minus 1/2 gt squared. We'll always have to keep track of whether we're in the English system or the metric system. So in this case, we end at y equals 0. If I call this my origin right here, I'm going to say 0 equals that, but I start at a height. So I'm going to say that that is 1.2. plus v sine theta times time. Sorry, I didn't mean to put that dash there. Minus 1/2 Our acceleration of gravity in the metric system is 9.81 meters per second times time squared. All right, we can keep simplifying this a little bit. I know the time; it takes 2.5 seconds. So let's go back to this side over here and solve this for. And this is our VA. Let's solve this for VA is equal to 50 on the numerator divided by 2.5. That's the seconds. And divided by cosine of theta. And that's equal to 20 over cosine theta. All right, then back on this side, let's see what we've got here. 0 equals 1.2 plus VA sine of theta times 2.5 minus 1/2, 9.81, 2.5 squared, and that gets us to 0 equals 1.2 plus. Now here's where we can do some substituting. Let's put this VA into that piece right there. So I'm going to call this 20 over cosine of theta. Scoot up that a little bit. Times sine of theta times 2.5. And then this evaluates at 30.656. All right, keeping on going here. This 20 times that 2.5 is 50. The sine over the cosine is the tangent. So again, I'll say that 0 equals 1.2 plus 50 tangent theta minus 30.656. Now I got something I can evaluate here. I'm going to say tangent theta is equal to 0.5891. Okay, so I did my algebra there, and theta is equal to 30.5 degrees. Okay. All right, so that's first piece of the answer. Now I can take that theta and plug it into either one of these equations and find out what our beginning velocity is. So I'm going to plug it back into that side over there, and I'm going to say that VA is equal to 20 over cos 30.5, and that's equal to 23.2. That'd be meters per second. And those are the two answers we're looking for. Now we may also want to find out the maximum height that the ball goes during the trajectory, and the maximum height is going to be at the peak of the travel, y max right there. And what we recognize is that the velocity goes in the y direction. Obviously the velocity is a constant in the x direction, but in the y direction it goes up for a little while and then it comes back down again. So at the peak of the height, the velocity in the y direction is equal to 0. So what we're going to do is use our y squared equation to do that, and we're going to say that velocity in the y direction squared is equal to velocity in the y direction beginning squared minus 2g, and that will be y max minus our beginning y0. All right, so again, we recognize at the peak of travel, that's going to be 0 at that, and we have in our y direction, we have 23.2 excuse me, 23.2 times the sine of 30.5. So 23.2 sine of 30.5 degrees, that's squared, minus 2, 9.81, y max, minus our y0, back to our picture, it would be I started at 1.2, and that's equal to 0. All right, I guess I did that on that side. And then I can solve that easily for y max is equal to 7, this piece of it here is 7.07 1.66 plus 1.2. So what I want to point out is that solving this divided by 9.2 times 9.81, it goes up an additional 7.066 feet from its origin, but to find out the top of the, so this delta distance is 7.066 meters, but then you have to add the 1.2 to get the total max. All right, and so the answer that we're looking for is 8.266 meters equals y max. All right, that gives you a little bit of an illustration of how to use that equation. All right, got one more I want to show you here, and plus give you a couple of hints. Don't have to do this one for you. You can see my work here, but let's imagine that we have a big gun on a ship that's firing a projectile a long distance away, and so let's say that it can fire the projectile at 2,000 feet per second. We don't know what the angle is. He wants to hit his target 20 miles away, so he has to figure out what that angle is. So again, we'll start with our standard equations. X is equal to Vx times time, so he's going 20 miles times 5,280 feet per mile equals Vx, so its velocity is 2,000 feet per second times the cosine of theta. Don't know the time yet. So I can simplify this and put this in terms of time. Time is equal to 52.08 divided by the cosine of theta. All right, in the y direction, he starts at y equals 0, he ends at y equals 0, so those are both 0. In the y direction, our velocity is 2,000 times the sine of theta times the time. And we're in the English system here with miles and feet, so I need minus 1/2. The acceleration of gravity is 32.2 times time squared. Okay. Now, rearranging this, we get this equation like that, and then I can substitute this time into here, and I get an equation that looks like this, with a sine and a cosine in the same side of the equation. And then on this side of the equation we get that. So you could probably solve this with a trig identity, and maybe find a quadratic equation. You can graph it, and you could probably find a curve where there are two roots that fit. Or you could use the solver on your calculator, which I encourage you to figure out how to do if you don't know already. But there are two roots, and that's the main thing that you have to take away from here, is that there's not one unique answer, there are two answers. Both of them work in this case, and you have to identify both of them. So anyway, here we are with I used solver on my TI-83, and I found out there were two roots, 28.49 and 61.5. Each one of those has its unique and own time. So if you fired it at 28.5 degrees, it would take 59 seconds to hit the target. And if you fired at 61 degrees, it'd take 109 seconds to get to the target. All right, so when you solve these things and there are two roots required, you need to identify both of them. The last thing I just want to point out is just a couple of helpful hints. I guess we've already done this maximum here. Let's look at this one here. There are several problems that you might need to find using an inclined plane. There's a couple of problems that are in our textbook where a golfer is on an inclined plane and he wants to land up something like this, and we may be looking for this distance or this length. Just as a reminder, use some trigonometry and keep the XY axes in the horizontal and in the actual vertical direction. Then when you identify how far it goes in the X direction, then you need to use this L cosine of whatever the angle of the hill is, and the height here would be the L times the sine of the angle of the hill. But the trajectory, the actual ball is being fired at, again, an angle not relative to the hill, but relative to the horizontal. So you have to keep track of the difference between the angle relative to the horizontal and the angle relative to the hill. Or the angle relative to hill would be that one. All right. Then the last thing that you need to know is that very common in these problems, students assume that the velocity when you end is 0, but that's not the case. You hit with a velocity. We're not trying to figure out what the velocity is after it gets buried in the sand or something like that. The velocity at the end has a value in virtually all the problems. So don't assume that the ending velocity is equal to zero. All right, well, that's it for right now.